The recording here. All right, hello everyone, and welcome to day 10 of Handmade Hero. We have made it through 10 days already. If you are following along at home with the source code from the pre-order, you will want to unzip source 9, source 009 from that zip file, because we are starting with source 9 here on day 10, and you can follow along. All right, welcome to Handmade Hero, the only show currently in existence that I know of in the whole universe where we code an entire game from scratch using nothing but our bare hands, our bare mitts. I know it sounds improbable, but we are going to do it, and we have been doing it, and everyone following at home has been doing it, and it has been fabulous so far. I see no reason to stop now. Now, hopefully, during the sort of warm up to the stream when the little countdown timer was on there, for those of you who joined a little early, you noticed that I conspicuously left a particular page here up for you to read. I don't know if you did. It's a little like summer reading assignment kind of a thing. Only by summer I mean the 20 minutes before the stream started. But what you can see here is the first time I've actually pulled this up. It's a great reference to be aware of. Now, it's a little opaque, it's true, but I love having it around. I keep a copy on my machine at all times. It is called the Intel Architecture Reference Manual, and you can find it online just by searching on the Google. If you go in here and you put Intel Architecture Reference Manual into the search box, you will get a link that basically has some kind of long-winded way that you gotta fill some stuff out, but I don't even remember how this all works. But you can eventually get to download, I think it's this thing right here, that's a PDF or something, and then when you open it, you get this nice thing. And what this is basically a manual that Intel puts out that really meticulously goes over all of the details of their processor. And you can look over here kind of in the table of contents. Basically, this Volume 2 one is the one that we're mostly concerned about, but the Volume 1 and Volume 3 are actually interesting to look through as well. They've got all kinds of stuff about like how the virtual memory works and how the various virtualization features work and how systems programming works, all of this stuff. There's all kinds of good stuff in here that you can read to familiarize yourself with x86 and x64 processor technology and how it works. But in here, Volume 2, the most important part, for any programmer who's just curious about how the CPU works, there's basically these two chapters, Chapter 3 and Chapter 4, which have an alphabetic list of all of the actual instructions that you can execute on an x64 processor. Absolutely every last one of them, I think, is in here. And so you can go through, and if you want to know something when you're looking at an assembly code, or you're just curious about what the processor can do, you want to know something, you can go in here and say, oh, we saw that MOV instruction on the stream, well, what's that? And they'll list every possible way that it can work, right? It'll have comments that kind of tell you what goes on when it actually occurs, and it'll have like sort of some pseudocode that says what the processor is actually doing internally. So it's pretty darn cool, and it's something that you should probably be familiar with if you're just trying to educate yourself a little bit about the specifics of how the computer works, which is one of the things that we try to focus on here. So the instruction that I had up was called RDTSC. Some of you may be familiar with it. What RDTSC is it's basically a way of getting at a register, it's really a performance counter, but it's basically getting at a thing inside the CPU that increments by 1 every time the CPU effectively like retires a clock cycle. So when you say that this is a 3.2 gigahertz processor, well, that means 3.2 billion cycles per second that the processor is executing. Each one of those cycles, this magical counter goes up by 1. And the RDTSC instruction lets you actually access the value of that counter at any given time. And the reason that I wanted to introduce this today was basically because we are going to look at some ways of figuring out what time it is in our code today. That's the thing that we're going to be working on. And this is a pretty important way that you can get that information, because RDTSC basically tells you the cycle count at any point in your program. So by asking for the cycle count before you do something and asking for the cycle count after, it gives you a pretty good idea of how many processor cycles have elapsed during the thing that you did. So if you want to know how many cycles it took to execute a particular piece of code, read timestamp counter can give you a pretty good idea. Now, it's not always perfect because there's a number of factors that come into play. The first factor is that not all operating systems save and restore the timestamp counter across task switches. So if your process is running and you're trying to time it, so you do an RDTSC at the beginning and RDTSC at the end, you're going to compare them, you won't necessarily know if the operating system woke up in the middle of that, swapped out your code, ran some other code, and then on the same processor, and then swapped in your code again for the ending RDTSC. So when you do those RDTSCs, you have to be aware that you're timing everything that the processor did in between those 2 points, not just the thing your code may have done. Now, this is, like I said, dependent on the operating system. Some operating systems actually try to save and restore the RDTSC, depending on how you access it. We'll kind of look at that a little bit later. There's basically like a query cycle. There's actually a call in Windows you can use. I think it's supported on Windows 7. Pretty sure. There's a call you can use in Windows that basically says, I want to know just for my thread, like just for this particular stream of execution, and that will prevent that particular problem from happening. But point being, things like that can happen. Other things that can happen is you don't actually necessarily know where those cycles are coming from. They don't mean instructions, they mean cycles. So depending on how warm the cache was, how much time it took to get memory, all these sorts of things, the RDTSC numbers are not going to be the same all the time. They're going to be widely varied. So you time a particular piece of code once, you're going to get one value. You time it again, even immediately thereafter, you're going to get different values because maybe things were in the cache that weren't before, all other sorts of things. So it's not foolproof. It's not a thing that magically tells you exactly what the performance of a piece of code is, but it is a thing that gets you some pretty raw statistics on exactly how many cycles elapsed between 2 points, and that is quite useful. So we will be showing how to use it. I just wanted to caveat it there at the beginning so that people wouldn't think it was too perfect. So that's the first thing we're going to talk about today in terms of timing. And we're also, well, I don't know if that's the first one. We're going to talk about 2 things today. The other one we're going to talk about is query performance counter. This is another way of figuring out what time it is, essentially. Again, this is all about clocking. Basically what this is a way of asking Windows and saying, hey, to the best of your knowledge, what is an actual wall clock time? So this is the processor cycle, and it's in terms of the processor's view of time. And what that means is that if we're counting cycles on the processor, we have no idea how that actually corresponds to wall clock time at all. When I say wall clock time, I literally mean like time out in the real world, the real time that you and I experience. Processor time does not work that way. Processors these days, depending on the processor, in desktop processors less so, but in mobile processors, definitely, they do a lot of clocking, changes in the clock speed to work around battery life and also to manage heat signatures even sometimes. So like, for example, if only one core is running, they may boost the frequency of that core, but if multiple cores are running, they might drop it, things like this. They'll drop the clock speed of a core when not much is going on to save battery life in a laptop. All of these sorts of things happen now on mainstream processors, which means that when you look at the cycle count, there is no constant meaning for how long that cycle may have taken in the real world. Because for some number of cycles, when you are using this RDTSC, you take your RDTSC at the beginning, you take it at the end of an area, you don't even know if the processor was executing at the same clock rate that entire time. It may be that somewhere in the middle of there, the processor downclocked itself or upclocked itself, and so the first set of cycles, each cycle took a certain amount of time, and then the second half of the thing, each cycle took longer or shorter than the ones in the beginning. So cycles really just tells you something about how much work the processor did in some sense, but it doesn't really tell you about the wall clock time. Query Performance Counter is the opposite of that. Query Performance Counter asks the operating system to please give you a high resolution, meaning so it isn't cycle accurate perhaps, but it is fairly accurate. It's not in seconds and it's not in milliseconds. It's something more granular than milliseconds, hopefully. Excuse me. Because you have to remember, if we're running at 30 frames a second or 60 frames a second, you're talking about things on the order of 16 milliseconds per frame or something like this for 60 frames a second, right? Because if you think about it, if you're in a handy, oops, why couldn't I? There we go. Need my little handy calculator. So if you think about it, if you have 1,000, a millisecond, there's 1,000 milliseconds per second, right? So if we're running at 60 frames a second, that's only going to be 16.66666666 repeating milliseconds that we have to do the work for any given frame. Each frame will be on the screen for, rounded up to 17, I suppose, somewhere between 16 to 17 milliseconds. Each frame will only be on the screen for that amount of time, and so that's the amount of time we have to do the work for the next frame. So if we're trying to figure out how much performance, how a particular piece of code gets improved or pessimized by a particular code change, and we're trying to time it, we, in general, need things that are going to be a lot more accurate than, say, a millisecond, because we only have 16 total of those, roughly, per frame anyway. So if it was on the order of a millisecond, even if we sped up a particular function by 20%, we would still get the same time back, potentially. It'd still be like, well, it took 2 milliseconds, then we sped it up by 20%, and it's like, yeah, it still took 2 milliseconds. It's like, no, okay, we need much more granular than that. So hopefully all these timers that we use are more than that. Certainly cycles is way more granular than that, because there's 3.2 billion of those per second when the processor is running at full speed, let's say. But Query Performance Counter is also going to be more granular than that. It's just not perhaps going to be quite as granular as a cycle count. But it is basically an attempt by the operating system to use some aspects of the system. I think it used to use some kind of bus clocking or something. I don't even know what it uses these days. I'm sorry, I have absolutely no idea. I've never even looked into it on a modern computer. But it basically uses some aspects of the system, whatever it can, to give you back some wall clock time. And you can see here that it's suggesting that its resolution is actually better than 1 microsecond, right? So that's much better than a millisecond, right? Just to give you something, millisecond per, microseconds per millisecond there. So you can see that basically you've essentially got something greater than 1,000 of those per millisecond. We don't actually know because it just says greater than. So it's something in this ballpark. So that's, in theory, going to be pretty high resolution for us to time things with. But the important part about this, as opposed to the cycle count, is Query Performance Counter actually corresponds to wall clock time. Meaning when we look at two Query Performance Counter times and we look at the difference between them, we will be able to actually correlate that out to a real world time. And that's important because it helps with your intuition. If we know that we have 16 milliseconds per frame to do something, it helps us to kind of know how much actual time is this particular piece of code taking. And we think about it, we're like, okay, it takes 0.5 milliseconds. So I roughly know I could do, 30 some odd of them, 30 something of them per frame. I kind of get sort of this idea of that, right? Where again, with the cycles, since they vary so much, it's harder for us to tie that back to a time. We always can, right? We always could actually try to time the RDTSCs with the Query Performance Counter so we know how many roughly the CPU is executing every frame and then back out those times and stuff like that. But really, without Query Performance Counter, we'd never have a way on a running machine of really even knowing how those RDTSCs map back to wall clock time, because we never would have any idea how fast the processor was actually running. We always at least need something that can tell us when a second went by, let's say, so that we could see, using RDTSC, how many cycles the processor had actually executed in that second, right? And so that's really where this comes in. So those are the two things that we're going to be talking about today, and I'm just going to show you a little bit about how you use them, and this will give us a little more insight as well into how our code that we've already written is even working. Because right now we don't even know, for example, how fast our program is running. We have no idea how many frames per second we're even getting, right? And this will finally let us kind of get that information. Okay, so I'm going to go ahead here and open up our command prompt. I'm going to get into Emacs, everyone's favorite editor. Excuse me. Still getting over the cold. Feeling better today, but still throat's a little scratchy. All right, so basically what I want to do here is I want to just start by doing something extremely simple. I want to start by saying, well, we have a loop, right? Here is our loop. We're gonna have a while loop where we just run and our game is sitting in this loop. I just want to start by going, let's print out some number that we can use to sort of see how long it took us to generate a frame, right? And in order to do that, I'm going to use this query performance counter thing because I want to know the actual wall clock time. I want to know how many actual seconds, and it's going to be fractional, it took to generate this. Or maybe we'll do how many milliseconds to make it a little easier to understand printout-wise, so it's not 0.00 whatever. Who knows? But when we get to our actual output debug string, we will actually, excuse me, print this out. Okay, so we have query performance counter. We're going to go ahead and get that, and we're going to call that. Now the way that it works is it's another one of these Windows functions. You've seen them a lot here, where basically they take something to fill out. In this case, a large integer. So basically we need a large integer, and we're going to call this begin counter, and we're going to take the address of that. And basically we pass an address in and it fills it out. Now a large integer, I don't know where, I guess there's no way to quick jump to it. I was going to show you the structure of it here, so I'll just cut and paste it into the search box. I want to actually show you the layout. There it is. So basically a large integer uses something called a union, which we really have not covered in this at all. It's a very simple concept. Basically what a union is it's just a number of things that are overlaid on top of each other in memory. So it's basically telling you that you can access the same piece of memory in multiple ways. So when you say union in C or C++, you then list things, and each thing listed in the union occupies the same space in memory. So basically this struct, and this long, which is long is Windows' way of saying uint64, basically, or int64, I should say, since it's not ulong. A 64-bit integer. Each one of these, right, is actually 64 bits, right? That's 32 bits, 32 bits, that's 32 bits, 32 bits, and this is 64 bits. Basically, this union is just 64 bits long. But you can access it using any of these methods. You can say .quadpart to access it as 64 bits. You can say .lowpart to access it as the low 32, or .highpart to access it as the high 32. You can also use .u.lowpart and .u.highpart. Now, why they wanted to do it this way, I don't know. This is called an anonymous structure, which means that these are directly accessible off of the thing. So basically, anonymous lets you access them directly. So I can just say .lowpart, right, like that, just with one dot. That directly accesses this. That's why it's called anonymous. There is no actual, it's not actually in here as a separate member. This u right here means that there's basically a field called u inside here that is the type is this structure. So if I wanted to access it through that, I would do .u.lowpart, like that. Now I have no idea why they have both of these in there. It doesn't seem like you would need them. They're both, like I said, they're occupying the exact same memory. So it's basically just to allow you to do that or that. So I have to assume that that's just for backwards compatibility purposes, like they made this one originally and then we're like, we should probably do it this way as well or something. I don't really know. But point being, you don't even have to worry about that. It's completely, it's some kind of weird anachronism, I would suspect. Since we are on a 64-bit architecture, we're just going to go straight for the quad part. The quad part is basically the part we want, so we're going to look at that. The quad part tells us basically whatever this value is, and we don't really know how to interpret this value. It's some 64-bit value that is a clock value that we know somehow corresponds to wall clock time. And now we know that begin counter.quadpart is that timestamp, that value at the time that we start the loop. So as soon as we ask for this, we basically now have that start time is in begin counter quadpart, right? So then what we're going to do is we're going to jump down. Well, actually, I guess we don't. We don't even need to do that. We're going to do it right here, basically. Right. So we're also going to say last counter, right? And we're going to ask for that up here. Excuse me. I figured this was a better way to structure this. I'll tell you why in 1 second, why I felt like that was a good idea. So basically, what we're going to do is we're going to say, all right, at the beginning, we're going to snap whatever the value is. Then we're going to go through the loop, and every time through the loop when we get to the end, we're going to look at what this is, and we'll call this end counter, right? End counter will give us another timestamp, and that timestamp will be how, after we've done everything, essentially, right? And then we'll go back down through the loop, and we'll get to end counter, and we'll get it again. So all we're going to do is every time after we actually print out here, right, we're going to actually display the value here. We're just going to say that the last counter, whatever that is, equals the end counter, right? So we're going to actually store whatever the value was here back into last counter. That will let us essentially compute the difference every time. Whatever end counter dot quad part minus last counter dot quad part, right? If I do this, and I'm going to put this in an int64, and this was the difference, time difference, right? You could say this was the time elapsed, basically. Maybe I should say counter elapsed. Excuse me. If you look at this, man, it is going to be so good to do this stream. I'm not sick. I've done almost the entire Handmade Hero sick. And it's really annoying. All right. It interrupts me. Anyway, so basically all we're doing here is we're saying, well, we have this clock. We're going to look at the clock before we enter our loop, right? Right before we enter it, let's say. We're going to do everything in the loop. We're going to look at the clock again. So we've looked at the clock twice. And just like in the real world, we can now take those two times, the beginning and the end that we looked at the clock, subtract the times, and we will get how much time elapsed, right, by that clock. So then, in order to make sure that works again for the next frame, we will pretend that now that original clock we took, that's just the new clock value that we got back. So that the next time we get back down here, we'll be differencing it from itself. We'll be differencing it from the last time it passed this point. And the reason that I wanted to do that, instead of putting a begin counter at the top of the while loop and an end counter at the end, is because, well, technically that doesn't quite capture all the time, right? If the actual act of getting back to the top of this loop, maybe the process got switched out or something happened that took a lot more time than just doing one comp and a jump to get back to the top, we'd miss that time. So I want something that's guaranteed to never miss any time. So by always using a single stable place where we check the clock and differencing it from that every time, we know that we've never had anything escape our time window. Our time window is all inclusive. There's nothing that could have happened that isn't accounted for within our clock window. So once we do that, we have a counter elapsed value that basically tells us how much time has elapsed. Unfortunately, we still don't know how to interpret this clock value. So if we want to print out how many seconds something took, how many milliseconds something took, we don't know. What we'd like to do is we'd like to be able to translate this back to human readable wall clock time instead of machine readable clock time, which we don't even know what it is because we don't know how Windows is even arriving at these clock values. But fortunately, they give us something that does exactly that. It's called Query Performance Frequency. Now, what Query Performance Frequency does is it basically tells us how many increments this clock goes through in 1 second, right? So basically, if we just ask for this up here, right, if we say, hey, Query Performance Frequency. Now, the question, I think, I'm going to double check this. I think we can just ask for this once because I don't think Query Performance Frequency is allowed to change. But let me see if they actually say that for certain somewhere. Let's take a look. Yes. The frequency of the performance counter is fixed at system boot time as it is consistent across all processors. Therefore, the frequency need only be queried upon application initialization and the result can be cached. So at least according to the documentation, which granted is sometimes wrong, we only actually have to ask once. So we can just say the performance frequency, or maybe I'll say the perf counter frequency, right, is going to be something we can just ask for. We then know how many of them happen per second, right? and we are good to go. So there we go. We now have that value, and we can use it. So if we actually go ahead and get that, right? Excuse me. I'm going to put this up here in the area. If we do that, we can then come down here and say, well, we have a counter value that elapsed. And we also know how many of those per second we're actually doing, right? We know that basically up here, in fact, I could even stuff this into a more useful variable. I could say int64 perf count frequency like this, and say that that was perf count frequency dot quad part like we did before, and this will be just a thing that uses to hold that value coming back. There we go. So now we have the perf count frequency. We know that is how many counts per second that thing is doing. So in here, when we have the counter elapsed, we can actually say, well, however many elapsed, right, divided by how many per second there were, that's how many, that's how many seconds actually elapsed. I just spilled my coffee, ladies and gentlemen. It was bound to happen eventually. Of course, thankfully, it kind of landed on my mitten, so it did not actually spill anywhere, but it almost did, and it almost wasted valuable coffee, which is really a crime. So doing this divide, saying the counter counts that we saw divided by the frequency of that counter gives us the seconds. And of course, one thing I should mention for the benefit of those of you who are maybe not math stars, I know I am certainly not a math star, so I just want to point this out for people who don't think about things this way, to maybe get you thinking about things in this way and doing a little more reading in this area perhaps. One thing I wanted to point out is dimensional analysis is particularly useful when you're doing these sorts of things, you know, in your head when you're writing this sort of code, just something to think about. If you have something like a counter and you say, well, I have a counter value and I know it came back, it was like X number of counts, right? Which is what we have. Like we got this back and we know that this is the number of counts that transpired, the number of like clocks that transpired, right? Number of counts, number of counter increments. And then we also know that this performance frequency thing, when we read the documentation, right, it says counts per second, right? So we also have a value that is counts, right, per second. So if you have two values, one that is counts and one that is counts per second, and you want to know how many seconds something took, which is this, right? But you have a value that's how many counts it took. The question becomes, how do you get that value, right? And the answer is you can always just look at how the units cancel on the divide. So let's say we were to multiply these two things together, right? What would we get? Well, just look at what happens with the units. Counts, this is essentially over 1, right? This is x counts and counts per second, right? If I multiply these together, I would get counts squared, right? Counts times counts over seconds, right? That is completely useless. That is not, count squared over seconds is, we don't even know what that is, right? So what you want to do is look at how do you actually cancel the counts, right, out like this so that you're just left with seconds, okay? And the way that you do that is you say, well, x counts, I just need this to be inverted. If seconds was on the top and counts was on the bottom, the counts would cancel. And that's what a divide is, right? A divide flips the two things in a ratio. So if I do counts divided by, right, counts per second, that is the same as multiplying by seconds per count, right? So the counts cancel and we're just left with x seconds, which is what I wanted. So looking at things in terms of flipping, basically flipping your ratios by either dividing or multiplying, you can line up a whole string of these things if you've got them and cancel all the things that you actually need, right? It's a standard kind of thing in dimensional analysis to do, where you've got some number, like you've got x seconds, and you want to know how many days x seconds is, right? And you can kind of just line things up. You can say, okay, well, at x seconds, I would need to multiply by how many seconds, I need to cancel seconds. So there's seconds, and I can translate seconds. I know how to translate seconds into minutes, right? Because it's basically 60 seconds per, 1 minute, right? And I know how to translate minutes, right, into hours, because I know there's 60 of those, right? So I can just say 1 hour is 60 minutes. I know how to translate hours into days, because there's 24 hours in one day, right? And just by literally going, well, whatever this thing was, I got to put it on the bottom to translate it into something on the top, put it on the bottom, translate something on the top. I made the math exactly what it needs to be. It's just multiply it out. X times 1 times 1 times 1 is X. 60 times 60 times 24. 60 times 60 times 24. These all cancel. Minutes, hours, hours, day, right? And we get this. And that is the answer. So you would just divide X by 60 times 24, and that is how many days it is. Again, if you're a math-minded fellow, this is trivial. But if you aren't, it's worth starting to think about things like this. There you go. Okay. Let's go back to the actual code, which I have not really been doing anything. Okay, so there's an end counter here, and there's a last counter. We got the frequency here. I got to put that in there. Let's see. Got to take the semicolon there. All right. So basically, this is going to give us back that value, but the question is, what are we going to do with that value? Well, what we can do with that value, certainly, is we can say, well, we've got the counter elapsed divided by the performance frequency. The problem is, if this is an integer divide, right, we know that the perf count frequency is how many counts per second there are, and we know that we probably didn't take a whole second to draw this frame. So this is just going to come out to 0. The integer divide, there's no fractional part, so something that's a large number divided by something that's a smaller number is just going to give us 0. So seconds is not particularly useful. So what we might want to do is say, well, if we multiplied this by 1,000, right, first, that would actually give us milliseconds now. So if we multiply this by 1,000, then we've got some room to do our divide. That would give us how many milliseconds it took to do this frame, right? So this is milliseconds per frame, right? That is the actual value. So now we actually know how many milliseconds per frame we're actually taking, and we can just take a look at how many that actually was. Now, of course, it's going to vary per frame, because like the first frame, we may do a lot of extra work. In the first frame, we may have a lot of Windows messages that come in that are like about initializing the window or something, right? So the first time we do it, we're not necessarily going to know, so we want to actually look possibly at later frames. Okay, so basically what we want to do is print this value out. Obviously, we have output debug string, which we can use, but we don't actually know, we've never actually seen how to print out a value. Well, we're going to look at that in a little more detail when we do the platform independent code. We're going to look at how to do our own output of values. So what we're going to do first is we're going to use Windows' code, much like we used Windows' sign function to just test our stuff. We're going to use Windows' code to output the variable as well. But later on, I want to show you how that works, so it's not a mystery to you how you output a number, because obviously someone knows how to do it since it works. There is a thing called WSPrintf, which you can use in Windows code to quickly generate strings. And basically all you have to do to use it is you create some buffer that it can write into, right? You can create some buffer like this. You can basically pass this buffer to WSPrintf. You can then give it some thing that you want to print out and give it the value that you want, and it will do it. Now the way that it does this is a little wonky, and it's just the way C's standard library originally did it, so it's the way Windows does it now. Basically what happens is it takes a format string, so it can actually be something like milliseconds per frame, colon. That's going to actually appear in the buffer. It's going to copy those characters to our buffer, right, that we've made here. That's 256 bytes long. It's going to put those in there, but then it's also, excuse me, it's also going to go ahead and look inside the string. It's going to process the string as it goes and look for anything with a % in it. If it sees a %, it will use the next thing that comes after it to determine what to print out, okay? And then the parameters that come after it, right, after the comma, it will then use to fill in whatever the % told it was coming. So if I say something, I've got like a thing here that once this is, we don't actually need 64 bits to store this, so we can actually do something like 32, and I'll tell you why in a second why I do that. %d, for example, is the code that says, hey, this is a 32-bit integer, basically. That's what that does. So this says I'm going to pass a 32-bit integer. Please replace the %d in the string with the 32-bit integer that I point you, right? And we can actually put a little ms after that for milliseconds, let's say. So in here, we can now just pass buffer, and that will actually do the printout for us. Now, there's a bunch of other things I want to talk about here, but I'm just going to see if we got this working first. Oh, I got to actually launch the debugger, of course, before we do anything else. So let's go ahead and do that. Here we go. So I'll close the app. We can kind of see what happened here, right? And much like I said, it's not particularly predictable if you look through here. The first frame was long, like I said it was going to be, not surprising. Then each particular frame you look at took us something on the order of 6 milliseconds, which occasional spikes up to 10 milliseconds. Now, normally those spikes, is that typical on this type of machine? I don't think it probably is, but you have to remember we are on this machine, all of our timings are highly suspect because we have this fine fellow, the open broadcasting software that is allowing me to talk to you on Twitch. You have to remember that it is doing a bunch of work to capture and compress this frame and everything. And even though this machine has an ungodly number of processors, I think I showed this in the intro to C stream, it just has an ungodly number of cores. It's 2-processor machine, each one has 6 cores or something like this, or 4 cores and 2 hyperthreads per core. I don't even know. I think it's 4 cores, 2 hyperthreads per core, 2 processors, something like this. I don't even know. We'll have to look it up at some point when we start talking about when we start talking about optimization in terms of processors, we'll start getting into stuff like what a hyperthread is and why you care. But for right now, just to say, there's tons of horsepower on this machine. It shouldn't be a problem. But the point is that is not necessarily the case when multiple people are contending for the same resources. Since we are blitting to the screen, we are copying our image up to the screen, and our runtime includes that effort, that ability to display things on the screen. OBS is trying to capture the screen from Windows. We may run into circumstances, for all I know, where there's like a lockup where we have to wait for it to do something and all. I don't know. I've never done any profiling of code that runs on a machine where video capture is running concurrently. But suffice to say, as we're doing the stream and doing timings, before we start doing any serious performance work, I will probably try to do some kind of outboard capture to get that out of the equation, because all of the timings that I take on this machine are going to be highly suspect until we get OBS out of there so that we know we're doing direct throughing, basically. But point being, what's interesting about this, and what I hope is pretty interesting to you just from looking at this, is this 6 milliseconds here. You remember 16 milliseconds, and I can print out this value as well. I don't particularly love frames per second as a value that's useful, but it helps because people quote it in the news all the time and that sort of stuff. But we can certainly put out that number, how many frames per second there are. So frames per second, right, is going to be the milliseconds per frame computation. Basically, it's going to be the same as that FPS here, right? Well, you know what? You should be able to do this now. You should not need me to do this, because I told you how to do dimensional analysis. So let's see. I'm gonna do this real slow, so that hopefully those of you at home who are going ahead will get it. I want you to get it before I do. Okay? So what did I say about dimensional analysis? I said that we want to look at what's on top and bottom of the ratios. So our target, right, is frames per second. Okay? And what do we now have, right? What do we actually have? Well, we've got 2 values we could work with. We have counts, right? We have x counts. We also knew how to translate that to seconds, right? So how do we get from here to here? I want x counts in frames per second, right? Now there's a little bit that I'm not saying yet. So see if you got it. Okay, hint number 1 is that this isn't just x counts. This is x counts per frame, right? because that is what we did. We timed one frame. So we know that X counts go by per frame. So counts on the top, frame on the bottom, right? Make sense? Does everyone have it yet? I don't know if everyone has it. See, the thing is, you can see me through the webcam, but I can't see you through the webcam, and that's really the problem. So I can't see if you've got it or not. But it's okay. So let's go ahead and take a look at this here. So the first thing that I would say, right, is I want to be able to invert this, right? I need frames to be on the top, right? Because frames is on the bottom at the moment, and that's no good, right? I also know that I want seconds. So really what I could do is I could say, well, first of all, we know counts per second. That was our query performance frequency. So if I multiply this, right? Oops, what's going on? Oh, I accidentally, did I hit some button there? That was interesting. It kind of froze me out, right? So what I want to do is I want to multiply this by something that's got like counts on the bottom, right? And seconds on the top, like this. How many seconds per count, right? And we know that that is basically the inverse of our performance thing. That would give me, because our performance frequency was counts, right? Counts per second. So the inverse of that, which is obviously, and I guess the one thing that I didn't say in that thing was, which is again mathy, so I suppose I should have said it, is that if I have some ratio, 1 over that ratio, like if I do 1 over counts per second, that gives me seconds per count, right? So I can always invert a ratio. I can flip it around by doing 1 divided by the value gives me the inverse of that value, flips the 2, right? So basically the most straightforward way to do this, right, is to say, all right, the first thing I want to do is I want to flip this around, okay? So I'm going to do 1 over this value. I'm going to take 1 divided by our counts per frame, right? And if I do that, then that will give me, I can't figure out how to actually erase this. I'm trying to, but I can't do it, right? Okay, there we go. So if I take 1 over this value, that'll flip it around, and that will give me 1 frame per X counts, right? Then I multiply that by how many counts, right, per second there are, which we know, this is our frequency, counts per second. This was the performance frequency, right? And so I cross out my counts, and I'm just left with frames per second, which is what I wanted. So we need to do 1 over our counter, right? We need to do 1 over our counter, that's this step. And then we need to multiply by the frequency, and that should give us our frames per second. Does that make sense? Hopefully that makes some sense. I don't know if it does, but if it does, there you go. So if we have 1 over the counter times the frequency, well, we can just multiply that out. That's just the frequency divided by the counter, right? Now, if you think about that, that makes some pretty good sense. That's basically saying we have, we have our frequency counts per second, our F counts per second, right, over our counts, right? And that just drops out the count values, which is sort of what we wanted. And seconds, of course, moves to the bottom because it's on the bottom. All right. Okay, so basically, dimensional analysis, play around with it. I realize it's hard if you've only seen it for the first time. That's probably not the best explanation anyone's ever given in the world. I can tell you that right now. Like I said, I'm not the math guy. So maybe take a look, excuse me, online for something like that, or maybe we can find some links to it. But basically, that's all we're trying to do here. So for frames per second, we basically just need to do our seconds per frame. I'm sorry, our what's our performance frequency? There it is. Our counts per second, basically, right? Divided by how many counts we actually had. Oh, there we go. Counter elapsed, right? Like that. And that should give it to us. I'm not sure. Again, like talking on the stream kind of makes. There we go. Okay. And then we close it. And then you can sort of see now this number translated into something that's more like what you would see reported in the press. So 6 milliseconds per frame is 143 frames per second, right? And we can sort of double verify that because if we've already computed the milliseconds that it took, we know there's 1,000 milliseconds in 1 second. So dividing by 6, there's that 166 value. Of course, this is going to be more accurate than that because it's actually a decimal here, 6 point something, something, something. And then there's the 7, which is a little bit lower value. So that is 1,000 divided by 7, and that's up in the 142, which is right accurate. So that was probably almost exactly 7. So that's basically, you know, I mean, that's really all there is to it. This is how you get a counter. There's pretty much, I mean, yeah, I think I've said just about everything there is. Dimensional analysis can come in to help you a little bit if you start getting confused about how to compute a particular thing. You want to look at those units, try to let the units help you, and that's the way that goes. Now this sort of thing is highly problematic. There's a number of reasons why this sort of thing is highly problematic. The printout I'm talking about here. There's so many ways that this sort of style of printout can go wrong. The first one is you can pass a buffer that's too small. There's ways of getting around that. Basically, if you go look up in MSDN here, obviously WSPrintf is documented here. There it is. Basically, there's versions of these sorts of things where you can pass in the size of the buffer to prevent it from possibly going over. Basically, I don't know, I guess they have these string CB printf here. Yeah. So basically, they have newer versions which do that, which do it. Here's an easier one to understand. So here's WNSPrintf. WNSPrintf is the same as WSPrintf, but instead of just taking a pointer to a buffer, it takes how long the buffer is as well, right? So instead, you could also point here, you could say size of buffer, like that, and now you know that if you pass in a buffer that's too small, you won't overwrite memory, basically. Because you have to remember, basically, all the original one sees, let's go ahead and, what, WNSPrintf, there, right. Not found. Why are you not found? It's right there. What's the problem? What is the problem? Oh, it's in some special H file. All right. I wonder if this will cause, this may cause us linked with something special as well, in which case I'm not going to use it. But let's take a look. Yeah. So I'm not actually going to use that. I'm just going to show this old one and say the fact that there is one that takes the size of the buffer. So basically, one of the problems with this thing is you pass it a buffer, but it has no idea how big that buffer is. So if you were to pass it a string that doesn't fit in the buffer, now we know this will always fit in the buffer because the number of the size of these two things can never actually be enough characters to make this get out to 256. So this is perfectly safe. But you could imagine if you made a mistake and you pass a buffer here that isn't big enough to hold the thing you're printing, you just overwrite the end of memory. Because it has no idea how big the buffer is. It assumes you gave it a buffer that was big enough. And if you didn't, off you go. That's definitely a source of bugs right there. Second source of bugs, and sometimes some compilers like LLVM will try to catch these by parsing the string at printout time. Basically, these percentage things are sort of just like assumed to line up with whatever you pass it. And this is basically a thing that does what's called varargs, which says the compiler just sticks whatever you put after the format string here. It just starts sticking these things on the stack, and then this function will just pull things off the stack based on what it sees here. But you could say that there was a ton of stuff that was never actually there, right? And the function has no idea that that happened. So it starts reading shit off the, I'm sorry, I'm not supposed to use colorful language. It starts reading stuff off the stack that it was never supposed to look at, that isn't even a variable potentially, that who knows what it is. It can do all sorts of things like that. If I told it that a pointer was coming, %s says that there's going to be a pointer to a string, but I didn't ever pass a pointer to the string, then you get into a thing where you'll do an access violation when it goes to try and read that. So it's fraught with peril. It's definitely fraught with peril. So typically, I don't use this sort of code in anything I'm going to ship. Like, this is not code that I like to see hanging around in like something I'm sending to an end user. I like to write my own versions of these things and know that there's some degree of accuracy to them if possible, and so on. But basically, if there is debug code or profiling code like this that we know is only going to ever really be run on our machines when we're developing it, then you can go to town, because a bug in there doesn't cost you anything. It's like, yeah, you crashed on your machine, or yeah, you had some security exploit on your profiled version. That's not that big of a deal. But if you're going to ship this to an end user, this sort of stuff becomes becomes dicey. It doesn't mean you can't do it. It just means that when you do it, you got to know, you really got to understand what you're doing. You can't just throw it in there and be like, I saw it on Handmade Hero and I just typed it. It's like, no, this can go wrong real quick. So you want to leave this kind of thing basically as debug code for the most part unless you really know what's going on. All right, so the next thing we're going to do is basically all we're going to do is augment that with that RDTSC thing that I talked about, right? So we're basically going to say, all right, when we do this query performance counter, I'm also going to go ahead and snap the RDTSC value. Now, thankfully, we can actually do that right from the compiler. There's usually an intrinsic for it, which I wanted to show you the documentation for, but I don't see. It's usually like underscore RDTSC or something like this that I don't see right now. Why am I not seeing it? Underscore RDTSC. What's going on here, people? There should be an RDTSC. On LLVM, it's that. That's what I used most recently, but let's see. So there it is. Yeah, why didn't it find that? Underscore RDTSC. Oh, I'm so sorry. I forgot that second underscore makes all the difference there. Okay, so it looks like that's all there is to it. Yeah, you just get, yeah. All right, so it generates the RDTSC instruction, which returns a processor timestamp. That's exactly what we wanted. We just want to call that function of the processor and get that value back. So basically, we're going to insert another thing here. We're going to say that there's an int64, which is the last timestamp counter from the processor, right? Or we can also say last cycle count, right? And basically, that will just be equal to whatever RDTSC was. And that just full on should output that instruction. Later, when we get down here, we're going to do exactly the same thing as we did before. So now we go to end cycle count, and we get it again. Then when we do our thing, and you know what, I'm going to do that since this is cheaper, RDTSC is cheaper than Query Performance Counter, I'm going to do that one first, because that's going to be the more accurate time there, I guess. Well, it doesn't actually matter because we're doing round trips time, so it doesn't matter. You can put them in either order because it's going to have to then go through this to do the rest of it as well. But point being, so then we're going to actually do here as well, we're going to do cycles elapsed, right? And we do exactly the same thing we did before. We do the end cycle count minus the last cycle count. That gives us that, and we do last cycle count minus, I'm sorry, right, equals end cycle count to set it so that next time through the loop we'll be using the most recent clock value. And then we know how many cycles elapsed it was, so we know the milliseconds per frame, and we also now know, and we can actually get rid of this because we actually said milliseconds per frame and frames per second, right? We're actually pointing out those values. I don't know, I'm not doing a very good job separating these. Let's do comma, comma, and then we want something here that we're going to print out, which is basically our cycles per frame, right, from the processor. And so the cycles elapsed is going to be a lot, right? So maybe what we'd rather do is say like megacycles, right? So maybe we'd rather do something like megahertz, right, like this. So we're going to say basically this is how many megacycles per frame we're actually taking, because otherwise, oops, sorry, that's divide there. So we're actually going to divide that out so that we're not actually looking at such a huge value. So we're going to say this is megacycles per frame, and we're going to grab this value out here like that, and then we are going to say that this is also casted down to int32. And the reason I'm casting these down to int32s is because %d is kind of a uniform way to print things out, whereas printing out a 64-bit integer using a printf style thing is only very recent. So %d actually always works on every C that you'll ever have, whereas printing out 64-bit can be a little bit dicey depending on the circumstances. So I'm trying to convert these to 32-bit values before I print them out. So hopefully that'll give us what we wanted. We can then go ahead and run this and see if that makes any sense. We'll stop it. And we can basically see here that, you know, in a given frame, we took 6 milliseconds and we executed somewhere around 20 million instructions to do that frame in the 6 milliseconds. So let's see if that holds water. Basically what we're saying there, again, if we take a look at the divisor, we're basically saying, okay, if we had 152 frames per second, right? So that's how many frames per second we have. So 152 frames a second times the number of instruction megahertz, megacycles, which was 20 there. That should come out to roughly the processor speed, right? And it sort of does, basically. And we don't know what this value's fractional is because we're not printing it out, right? So there we go. We've got that. And if I look at the actual, I don't actually know how to get to this anymore. I always forget. Where is it? If we look at the clock speed, we should see it's like, yeah, okay, so it's roughly around there, right? It's 3.19 gigahertz. And so that's roughly in the ballpark of where it should be. And I think if we did a little more precision there, it should come out. In fact, we could actually do the math with the actual original values and see what it actually was. We could say, for example, we could do the milliseconds per frame times the cycles elapsed or something like that. So basically that there tells us all the clocking information that we want to know, just not to very high precision. So the next question is, could we do fractional? And the answer is yes, we can do fractional. We just have to learn a little more about how you do printfs. Now, if you want to do fractional, you have to use the C runtime library, because if I remember correctly, WSPrintf, the thing that's built into Windows, cannot print out floating point values. It just doesn't have the ability to do so. That's my understanding. Yes, it does not. Because this is basically a listing in here of all the things that WSPrintf can take with that percent thing, this percent thing here. And you can see all the stuff that you can say, right? There's like signed characters, signed decimal integer, signed shorts, unsigned shorts, blah, 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 blah. But floating point value, like we learned about yesterday, nowhere to be found. So if you want to print out a floating point value, you're kind of out of luck. And if we want some kind of fractional value that says the fractional milliseconds, we can't actually do that. Now, obviously, one thing you could do is just not use numbers that you have to see fractions for. But if we want to see a nice fraction, like a fractional milliseconds, so 6.23 milliseconds per frame, we actually need to use the C runtime library's version of the same function, which is just printf. So you can see here, there's WSPrintf is Windows version of the printf. If you want to, you can use the C runtime library's version, which is printf. Again, I don't really want to start relying on libraries too much, so for debug code, this is fine. I'm just telling you that it's there if you want to use it. So you can, if you wanted to do that, you can use sprintf instead of WSPrintf, but you have to go add up here a reference to standardIO.h. That's the C runtime library's function. We're already linking with the C runtime library, so all those functions are technically in there, and you can all call them. That will do exactly the same thing. So if we run it now, there's no difference, right? Basically, we take a look, and there is the same exact printout that we saw before. But we can go in here and actually use %f, which means print out a floating point value if we want to. And we can also use some things called format specifiers. So if I just do %f and change these all to %fs, then what I can do here is do all of this in float, right? I can do all of these values in floating point, and I can just instead of doing them in integer arithmetic, I can do it in floating point arithmetic and get all of that stuff that we wanted here. I can just go ahead and say that all of these things are floating point values, and then we will essentially have everything computed in floating point like that. So there you go. If you can see that. Basically, if we do it this way, there's a little bit of a caveat here that I'll tell you about in 1 second. But when we actually print these out, so many things to talk about here. When we actually print these out now, we will actually be able to print out floating point values. So now when we see it, you will basically get something that looks like that. Same exact printout, but now you notice we've got a lot of fractional precision there. And presumably, like I was saying before, now if we actually look at the math, it'll come out a little bit better. If we do 147 frames per second, right, and we do that times the number of cycles, megacycles per frame, multiplied by, you see we get almost exactly that CPU number, right, which is what we were expecting to see, 3.19, which is exactly what we wanted. All right, so anyway, hopefully you can sort of see how that works out. I don't want to belabor this too much because, like I said, these are just some standard library functions that exist, and we're not really going to be using libraries much at all in this stream as we build the game, since we're trying to build everything from scratch. So I don't really want you to get hung up on how to use the C runtime library. But again, it is all in there for getting your debugging code running I mean, when I go to write a platform layer, even when I am writing everything from scratch, I will often use something in the standard library of that platform or the operating system to get my stuff going. So I basically know, that it's some reliable code that I didn't just write myself from scratch. Now, the other thing you can do in here too is you can add format specifiers. Again, if you want to, in here, if you look up the definition of sprintf and stuff, there's a thing usually somewhere that, okay, here it is. There's a link to say format specifications. And you click on that, and there'll be a whole big document that says, here is the thing that you use for those percent things. Here's all the stuff that you can put in there. You can look at all these things like flag directives and so on. And basically what they all are is they're ways of encoding into that percent notation how you want the value printed. So for example, if I say 0.02, right, I can control the degree of precision and how the floating point number is printed out. Remember, it was printing it out at this precision before, 6 decimal places. And that's maybe a little too verbose for me. So if I specify 0.02, it says, I want you to go ahead and actually print out the number to 2 decimal places, right? You can see there? I don't know if you can see that. So, if you want to learn how to do this, it's not a waste of time. You can call these when you're on a platform trying to get things working. They exist everywhere. Anywhere that you have a C compiler, you have this function to call with the C runtime library. Kind of like we were able to call sign. That'll work everywhere because the C runtime library is built in. You know that a compiler has to ship with it in order to be like a standard compliant compiler. So you know that you have access to these when you're getting your debug code working. Even if you're doing everything from scratch like we will be, you always have those to fall back on if you're trying to test, or you have bugs and you're like, what's wrong with my code? You can call their sign function and find out why your sign function doesn't agree with it. Stuff like that is very useful. So again, I don't want to try to tell people never touch a library and you're like a bad programmer or something if you use libraries. Libraries are totally fine. We just want to go through and show you how to build everything. So later we're going to actually look at how to do our own kind of printfs and stuff. Which are actually kind of complicated. We're going to look at some things like that as well, just because I want to show you how that does so it's not a mystery to you how it's doing stuff like this. So that's basically everything about timing. And what you can do now, and this is something that we'll do a bit later when we get to profiling, is in the platform independent layer of the code, we can also build a little bit of a superstructure that calls into the platform layer, the platform dependent layer, to get timing information at various points in our code. So we'll be able to see who is taking that time. So we timed the whole thing, right? But you could imagine us doing something a little bit different, where, for example, we could query the performance counter right here as well, right? We could say, let's take another performance sample right here called mid counter, right? Like this. And we could take a look at how long it took us to do everything but that stretch dibits, right? This is where the stretch di bits happens. How long does it take to do everything up to that point, right? You could do that, and you could come in here and say, well, the amount of counter elapsed, we could do the exact same thing and see how long that takes. That is the kind of thing that we'll be doing when we get into profiling. We'll have some nice utility function we can call to just drop stuff into our code and see how long every individual thing takes. How long is stretch dibits? How long does it take us to build our gradient? How long does it take to fill the sound buffer? Those are all the sort of things we'll look at when we actually start to look at profiling. But that's really all there was to it. Now that you have those tools, you can build any kind of profiler you want. We'll see, some interesting tricks for doing that. But that's it. So anyway, we've come to the end of the stream, and it is time for Q&A. Thank you so much, everyone, for joining me for another Handmade Hero. I hope that that was all relatively clear. I know it can be kind of confusing with all these sort of things. Hopefully the clocking stuff was clear. This guy, like I said, this is a whole topic unto itself, these printfs. So if you're a little hazy on that, I don't blame you. Like I said, I don't really want to harp on it. It's basically just a simple way you can use to print stuff out. Any tutorial you read online about how to use printf, and basically there's a bunch of variants. There's like printf, which prints something to the console. There's sprintf, which prints something to a buffer. There's a vsprintf, which allows you to pass through printf things. There's a whole bunch of different things like that. There's fprintf, which prints things to a file. There's the whole suite of those in the C runtime library that basically are provided courtesy of the compiler for you to call if you want to. So there you go. So yes, with that, I'd like to go to the Q&A. Please remember to prefix anything that you want to ask with @CMuratori so that I will see it. Someone's saying RDTSC returned an unsigned integer. That's what I would have thought too, but I thought maybe I was just quickly reading it. I would have thought it returned an unsigned integer as well, but for some reason it looked like it didn't. I don't know why. Oh, it did. Okay. I was asleep at the switch. Yes, thank you for catching that. That was odd to me as well. I was like, gosh, that's weird, because I have always in the past stored it in a uint64, but I was like, well, maybe I just want to follow thing. Okay, good. That's good. Cycle count. There we go. uint64. There we go. Cycles elapsed. Yeah? There we go. Okay. So that's really all we needed there. Oh, so one thing I should talk about really quickly too, while we're in the Q&A. You'll notice I went in here and I had to cast these things to floating point values. The reason for that, and we kind of glossed over it, we didn't really talk about this in detail, and I should just mention it for people who are not as familiar with C. Maybe you're coming from this to the stream from a different language, and you may not understand all the implicit rules that C does. So one of the things is, if I have two integers, right, I have int x and y, and I say x divided by y, right, it's going to use the types of those integers to determine what kind of divide to do. So even if I was trying to store it in a floating point value, it doesn't really look yet when it does the divide. It doesn't look at like what it needs to generate at the end of the equals. It doesn't use that to determine what kind of divide to do. So these are integers in memory, and they're integer types in C, right? So C is going to do this as an integer divide. And an integer divide produces another integer. And of course, an integer has no fractional part. So the fraction just gets thrown away. It's gone. So if we did float z equals x divided by y, we will get no fraction, even though this value is capable of storing a fraction. So what you have to do first is tell C, using the casting notation that we learned, basically we have to tell C, cast this, convert it first to a floating point number, then do the divide. And then C understands, oh, okay, I see what you're doing. We're trying to move these into floating point registers, do a divide in the floating point registers, and then store the result of that floating point divide out to the float. Oh, yes. You know what? I still need to figure out how to put a window up there. I was using an index card. I'm sorry I was drawing behind my window in Paint. There's a little, I gotta make a thing that blocks my screen just out. I've been so good and I forgot. So someone is asking, let's see, where are we going here? Someone was asking if we can compile with optimizations on and see how this changes. So that's true. If we were profiling our code, obviously, we are not turning on the optimizer here. So basically, the compiler is producing the slowest possible version of our code right now. It's not trying to do any thinking about how to make the code fast. And that could matter because, again, we've got some large loop things happening here. Like in our thing where we render weird gradient, there is a lot. This is going to be 1280 by 720 or whatever we said our window height was. We're going to be operating on a lot of memory here in our little loop. If the compiler were to optimize this or not optimize it, that could make a difference. That's definitely true. So basically, if we take a look here, I don't really want to get into performance analysis yet. So I'm not really going to harp on this. But since someone asked the question, we could look here and say, well, here is just a poor man's quick version. We could look here and say, well, all right, so here's the thing unoptimized, right? That's the sort of typical thing that we were seeing unoptimized. And then we go into our build script. We can say we want it optimized. That would be in build.bat. We can pass -02 to it, and it will do some optimization for us. And then we'll hit F5 and see what it actually is. We close it, and now we can see what we actually get for our frames per second and see how they compare, right? Our milliseconds per frame and so on. So this is optimized, right? And as you can see, the unoptimized version is pretty consistently about twice as slow as the optimized version, right? And that's not perhaps atypical in a circumstance where we have not optimized our code at all, so it's entirely up to the optimizer to do everything. That's totally reasonable, right? If it's code that we've optimized, we would probably not be getting a 2x like that because we've already done a bunch of work to make the code sort of more optimal as it is. But yeah, so hopefully you can see that's basically this is with -02 and this is without. So that's how that works. Let's take a look here. Okay. Do the divide in doubles. Oh, yeah, I should mention that. Thank you for saying that. Someone was talking about the divide here. So I wanted to mention this as well. I kind of said it as we went through the stream, but I never actually showed it. So one of the things that's true here is if you really cared about the last little bit of accuracy, so you, like, at this level of accuracy, you don't care about this at all. But if you were printing out a more fine, if you wanted more decimal places here and you actually cared what the value was, you're actually trying to be more accurate and not just a rough idea. The thing to remember is basically a 32-bit floating point value, as we covered, has 24 bits of accuracy in it, right? We said it was 24 bits of mantissa and then 7 bits of exponent or something like this. I don't remember what we actually looked up what it was, but it's basically that. So it's 24 bits of accuracy, but we've got 64 bits of accuracy coming in. Now, technically, after this subtract, there's actually not going to be that many. So the person who said do the divide in 64-bit, I know where you were going with that. It probably won't change the result at all because you don't have 64 bits of accuracy after you do the subtraction. But let's say that you time something really long, right? So instead of 20 million coming back, like this is 10 million coming back. 10 million, you're not going to really lose any accuracy doing a floating point divide at 10 million. But let's say you would time something that was like 50 billion cycles. It was several frames long or something like this, right? Then doing the divide in a 32-bit float, it'll still work just fine. But you'll have a lot less precision because 50 billion is much higher than the number of decimal places that you can have, the number of bits that you have in your 24-bit float. 50 billion would be like, 35 bits to represent all the things in there, right? And we only have 24 bits of mantissa in our floating point value. So in order to actually do the divide out all the way so that it was actually as accurate as the numbers that were going in, you would want to cast these to real 64s. You'd want to use 64-bit floating point values. For what we're doing, we're never going to have a big enough thing that we ever actually really care about that. But if you want to, you totally can. And one of the things that's a weird, total anachronism, quirk, weird thing about printfs is they always actually do the printf in double anyway. Basically, they always use 64-bit floats. So these actually get passed as 64-bit floats anyway. They get up-converted when they get passed at the end. So you're actually, if you want to, it's more or less free to do it with the additional precision because you're only doing this once, and so it's not like it's some big thing, and it's only for performance tuning, so you're not even shipping this code. So it's not really a big deal. You're not doing it that often. You can, for free, if you want to, just do it with higher precision. Now, you're not going to see any difference. They're going to be exactly the same in this particular thing. But if you were doing stuff, it might count. So it's free if you want to do it with the higher precision. That's just something to think about. Let's see. It would be nice to have a roadmap so we can read ahead when you deal with string formats, threading, OpenGL, DirectX, cross-platform stuff, etc. And would I consider doing a 24-hour stream today? Roadmap probably won't happen. And the reason for that is that I don't think they're a good idea. Not because I don't want you to know what's happening, but more because programming with a schedule never works. You have to be able to sort of feel, you have to be able to build up a good intuition about what the thing is that needs to happen next after you do each individual thing. And if you have a roadmap, then you're sort of saying that you're going to do whatever the thing is that was on the roadmap next, but that may turn out to be inappropriate. So there will not be a roadmap. That's not going to happen. At best, I will start to tell you as we go into the later parts of the code, and I have done this already, what we're doing the next day. So if you want to read up on something during the day for the next night's stream or something, that might happen. 24-hour stream probably won't happen. Will we be able to use a PlayStation 2 controller? Yes. I mean, at the end, we'll make sure we work with all sorts of things. I don't know about PlayStation 2 controller specifically, but at least a PlayStation like 4 controller or something, some PlayStation controller that plugs into a PC, we will test with and make sure that we get it working with that. Let's see. Can we expect more Jeff and Casey shows in the future? There's one every Monday. There was one just this past Monday. There'll be one this Monday as well. You can always get more. Just subscribe to the podcast stream and you get one every Monday. Is it safe to use 64-bit variables and functions on a 32-bit PC? Yes. It's just not safe to assume that they are performant. So basically, if you do some kind of 64-bit operation on a 32-bit PC, you may end up in a situation where you're emulated. So basically, the processor generates a bunch of things to do a 64-bit multiply or divide. It may be very inefficient. As long as you're doing them only in places where you don't do them a lot. So this is like 1 per frame. You could afford 10,000 cycles to do this subtraction if you wanted to, right? And we're immediately up converting them to floating point values to do the rest of the math. So we're only literally doing subtraction of 64-bit here. That subtraction will never hurt you, no matter what processor you're on, pretty much. So that's okay. If, on the other hand, you were in some tight loop that like let's say in our pixel loop that we're actually filling our gradient out, if you started doing 64-bit math in there, that would be real bad if you then tried to run it on a processor that couldn't do 64-bit math natively. That would be a bad scene. Let's see. It feels like even though we are doing low-level programming, sometimes we have to pass things to Windows. It makes it difficult to follow exactly what the computer is doing. Will this change when we move on to other platforms, or will we also run into the same problems occasionally? I would say basically that is just an endemic problem with modern programming. Basically, one of the reasons that I did this Windows platform layer first is because now that we're basically done with it, there's one other thing we'll do, which before we go a little further, but we'll do that next week, integrated with other things, which is file I/O. But basically, the reason I want to get this out of the way first is because from now on, we'll always be able to know exactly what's going on. But there's always this bottom substrate that you don't know what's going on. And it's unfortunate. When we do the Raspberry Pi port, we'll be able to have a lot less of that. But even then, we'll still have like a little bit of firmware. You never, unless you actually built the firmware for the machine that's actually in the ROM, there's always some call you eventually make which triggers some code someone else wrote. Even in the DOS days, you would trigger an interrupt to do I/O or something like this. You didn't actually write that exactly. You didn't burn the EEPROM in there, which talks to the the IDE controller or something. So there you do have to, unfortunately, even though we're going pretty low level in the stream, you do have to always be used to the fact that at some point, someone else does take control of things. Even if you were to burn the firmware yourself, you'd still be in a circumstance where there's microcode executing on the CPU and you didn't write that. So there's always someone below you and you have to be comfortable with that. What we try to do on the stream is go as low as reasonably possible so you can see everything you might want to control and that you could control. But in terms of actually getting all the way down to some pure level, there really isn't one. So you're always going to have to draw that line somewhere. We are basically trying to draw it as low as feasible so that you understand everything you might ever care about, basically. But we're not going to try and go down to a level of absurdity where we're like, let's try and microcode our own, let's make our own CPU and have it fabbed and then program on that, right? You could go that far. We're not trying to do that. Let's see. Do you ever use a profiler or mostly use hand-coded timer calls? I mostly use hand-coded timer calls, but sometimes a profiler can be useful. Why do I use Pascal case for everything? That's just how I tend to program. I don't have a why. Like how you name things is not really a why. It's whatever is most comfortable to you. Is it a violation to set one member of a union and then read from another? No, that's totally legal. Or at least it works on every compiler I've ever used. I was playing around with the input code yesterday with a DualShock 4, and so I started thinking about when we would get around to implementing raw input so we can handle those controllers natively. Probably not for a long time, actually, because I don't really want to spend a lot of your time looking at platform code, especially because I'm showing you how everything works, but I'm not like telling you have to do everything yourself. Like if people want to use the simple direct media layer or something, SDL, right, or whatever, that's a totally fine decision, and tons of people ship games on those things. So the goal here is not to teach you that you should implement an entire platform layer yourself. The goal is to show you how to do that so that you understand how everything is working when you choose to use someone else's library or any of that stuff, or so that you can write a better version of SDL yourself if you chose to do so, right? So that you have the ability to write all that stuff. So I really want to focus on the game code and all that stuff more, because that stuff is important no matter what you're doing. That's something you need to know regardless of how far down the stack you choose to go. So we won't do like raw input or something like that till way at the end when we do the shipping version of our Windows platform layer, which will have raw input and overlapped I/O and all these other sorts of things. But we're not going to focus on those now. We're just doing the minimal Windows code now, and we'll do the hardcore Windows code way later, like when the game is done. Modern CPUs, RDTSC returns nominal clocks, not real clocks. That's Tom Forsyth, who, by the way, if people don't know, actually is someone who worked on, for example, the Larrabee project with Intel CPU team. He was at Intel for a while. So he is more of a processor expert than I am, certainly. Unfortunately, Tom, I'm not the guy to try and explain how clocks get returned, because I have no idea. Like basically, I don't know what a real clock is in the CPU versus a cycle in terms of what it's going to tell you. So if you, Tom, want to post a good article about this, because I know you have a blog, I would be delighted to point people towards it tomorrow. Well, not tomorrow, on the next stream on Monday. I'm not saying you have to, but if that's something you would like to clarify for people, I would be happy to point to it, but I'm not the guy for that. I don't know CPU architecture very well, so if I tried to explain exactly what a cycle in the CPU was versus a cycle in RDTSC, I'm just going to get it wrong. Plus also the modern CPU thing, I don't know where that modern change happened. Like I know the Pentium introduced the RDTSC, but I don't know where the changeover happened from real clocks to nominal clocks and so on. Why are you avoiding doubles in your code? Well, I never use doubles really because they're much slower than reals. So sometimes in timing I would use them, but again here they're not necessary at all. They would be completely unnecessary for the computation we were doing. So I only use doubles if they're absolutely necessary, and in this case they weren't. And that's because they're half as fast usually, right? You can do twice as many float operations as you can double operations in the same amount of time. That's just how that works. Are you opposed to ever using high-level languages when making games? So I'm not opposed to using high-level languages. I'm not opposed to programming at a high level. I'm opposed to high-level languages because all the ones I've seen are lousy. If there was a high-level language that worked the way I want a high-level language to work, then I would be super in favor of it. But all the high-level languages I ever see are awful, and I would never program in them. Let's see. If you want to lock the FPS at a particular number, would you just sleep or do something more complex? Well, the easiest thing to do there is if you can wait on the vertical retrace. That's the easiest way to do that, and you can do that with direct direct draw still. You can still, I think, get a handle direct draw and wait for the vertical blank. When you are using Direct3D or OpenGL, you can usually tell the swap command to wait for the vblank. So the easiest way to lock to the monitor refresh frequency, which is what you presumably were asking that question about, that's the easiest way to do it, because then you know it's actually locked to the monitor, which is what you would rather do than try to fake that. But if you want to lock to a particular frequency on your own, then yes, you would sleep. But before you can sleep, since sleep is 15 millisecond granular on a lot of operating systems by default, on a lot of Windows versions by default, you have to do a thing called you have to set the scheduler wake up frequency and stuff. So you have to call time begin period. There's a whole bunch of stuff you have to do. So we'll look at that a little later, but it's not as easy as just calling sleep, I guess is what I would say. You got to do sleep and a spin lock, and you got to tell Windows that your sleep is millisecond granular. Let's see. Isn't RDTSC affected by variable speed technologies in modern processors like SpeedStep? So it depends what you mean by affected. It sort of is and sort of isn't. Like, it depends what you were trying to get out of it. So yes, the answer is it's definitely affected. And I think I talked about that when I was talking about the fact that there was like all sorts of things where like it could change in the middle of when you were timing something, it could change the CPU frequency and stuff like that. That's what I was talking about. Unfortunately, again, I'm the wrong person to really say how that all works out. So like, for example, for all I know, in the latest CPUs, they may do stuff like pretend the RDTSC is always at 3.2 gigahertz, even if the processor downclock. Like, I don't know what they do now. I have no idea. All I know is what it says in the Intel architecture manual. So all I know is what it says here. I don't know anything that's not in here. So if you really want that answer, and this is maybe we'll be lucky in Tom Forsyth, since he piped up in the Twitch chat, maybe on the hook now. You want to ask a processor expert to tell you exactly what happens there, because I don't know, and I don't pretend to know. I use RDTSC as a high frequency profiler tool because I know that I can use differences in it to know if my code was getting faster. I don't try to use it most of the time for doing the kind of really precise optimization work where I actually want to know how many actual cycles really happened. I don't do that. So I've never had to really go figure out on a modern, like on a Core i7, let's say, what that actually means. Have I done Ludum Dare? No, I have not. And no, I probably would not be doing that. Let's see. Let's see here. Can we do a bonus stream on ASM? We will actually be doing assembly language in the stream as far as intrinsics are concerned. We'll be optimizing our code with intrinsics. An ASM stream, again, much like I'm the wrong person to tell you about exactly how CPU cycles get retired and reported, I'm also the wrong person to tell you how to program assembly language. I understood Xbox 360 assembly language extremely well because I wrote an assembler optimizer for it. That is like the only assembly language I really know how to program at all. I know how to read x86 and x64 assembly language because I need it for debugging and I need it for like looking at what the compiler did. So I can sort of read it okay, but I don't have the kind of experience that I would want to have before I would sit up here and try to tell you how to program an x64 assembly language. So I would love it if someone like Jeff Roberts did a assembly language programming stream. I don't know if he would, probably won't, but like I would love it if someone who was an assembly language programmer, who did a lot of assembly language programming would do one. That would be fantastic, and I would watch that stream, probably learn a lot from it. But I'm just the wrong assembly from scratch is just not. I don't have the experience for that, and it would not be a good quality education for anyone. Let's see. If you read the latency tables for SSC2 float versus double, you'll see that double isn't that much slower than float on the CPU. It's half as fast, dude. You can do twice as many floats in a register as you can doubles. What are you talking about? I'm not sure what he's talking about. I'll look at the Agner Fog tables. You're talking about these tables, right? Let's see here. This is Agner. So this is Agner Fog. He's a guy who posts a lot of good optimization stuff. He does like performance analysis on x86, x64 processors. And he basically posts a bunch of these things here. You can see, like, for example, there's instruction tables, list of instruction latencies, throughputs and stuff, and micro-op breakdowns. So you can jump in here and see, basically a bunch of information that's not in the architecture reference manual. So, you know, if you go through here, you can find, I guess those would be in the P, I don't even remember what the double instructions are, but these would be down in the P, pmol. So there you go. So yeah, I mean, basically, let's see here. So is it actually reciprocal throughput? Let's see here. What are the instructions we want? So that was, what was that? That was a divide. So you're saying that the floating point divide should be the same speed as, you think it's the same speed as the floating, or not the same speed, but roughly the same speed as the double width divide. So let's take a look here. Where is our P reciprocal? Well, I guess we can look at multiply first. So where is our multiply? It's like P mol something. So P mol, where are you? Let's move. Okay, how come I can't? There we go. So where are we here? That's the integer. You can tell the last thing I did was bink. I immediately go look at the integer instructions, which are totally not what you actually wanted. Let's see here. Let's see here. Sorry, we're kind of, the stream is technically over at this point, but it's an interesting question. We might as well look it up here and see what the actual stuff is. Instruction set for SSE. What are the actual things here? Those are packed integer. What is, do you know what the instruction is? Tell me what the instruction is for double. If someone on the stream knows what the multiply instruction is for double, so I can look it up more quickly instead of having to look it up on the stream here, because I don't know. I don't think I've ever actually admitted that I've never asked for that intrinsic in my whole life, so I have no idea what where it actually is. Yeah, what is it? Tell me, who on the stream, someone must know what the intrinsic is, what the actual instruction is for doing a double multiply, a SIMD, an SSE double multiply. Here we go, mul PD, there we go. I don't know why, so I am used to using all the P SSE ones because I have to do a bunch of integer work when I was working on Bink, and that was the most recent SSE thing that I did. So here we go, so mul PS, mul PD, that's what we want. So packed single precision floating point values, packed double precision floating point values, mul PS and mul PD. So now if we look those up in the table, presumably these are still in alphabetical order. No, they are not in alphabetical order. They are by type. So let's see, arithmetic instructions, other floating point, there we go. Floating point XMM instructions, where is our mul? Well, you know what? Maybe I'll just search for it. Mul PS. There we go. So mul PS, this is on an AMD, so that's probably not so good. Where is x64? Let's see. That's the K8, K10, Bulldozer, Steamroller, Bobcat, Jaguar, Pentium 2 and 3, Miram, God. Ivy Bridge. There we go. Let's look at like Haswell, for example. That's a good one. So these are just basically all the cores. Sorry, this is probably not that interesting to most of the people on the stream, but basically all we're doing here is we're looking up in the instruction tables, which takes a while. We're looking up how long it takes the CPU to do operation on a double versus operation on a single floating point. So basically like 32-bit floating point versus 64-bit floating point. So these are broken down by core because obviously Intel ships a lot of different versions of their CPUs. So there's basically, if you think about it, there's basically lots of different potential throughput values, how fast the processor can do something, depending on which processor it actually is. So what we want to do here is we want to take a particular core, a relatively recent core like Ivy Bridge, right, which is a relatively recent Intel core, and take a look at how it does a mul PS, which is a single precision floating point multiply, versus a mul PD. So basically what I want to do is I want to search down through here, so presumably it's somewhere right here. That's Haswell. Why can't we see mul PS? Mul PS. Mul PS. mul_ps. I don't know why I can't see it, because I'm searching for mul_ps, and this is where it is. For some reason, it says it's there. I can't actually see a mul_ps there, right? Because it's supposed to be showing on the page right now, but where I don't see mul_ps anywhere on here. So let's take a look. Mul_ps, 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 mul_ps. Okay, Ivy Bridge. Mul_ps. So it's single cycle. Is that correct? Single cycle. And mul_pd. And what's this single? Wait, what's this column here? Hold on a second. What are our columns here? The latency. So if you want to do one, and reciprocal throughput is here. Okay, so that's what we want to see. So basically, the latency is from when we issue the instruction to when we get it back. How many cycles will it be? So if we issue one, when do we get the result back? And reciprocal throughput is basically how long it takes to get them. How should I say it? It's basically if we issue them every clock. So if we just kept issuing them one right after the other, then sort of how long would it take to do each incremental one? So basically, like if it takes a latency of 5 to do it, but we can issue one every clock, we'll start getting them back every clock that we issue. So we could still have essentially an effective throughput of one, even though we technically have to wait 5 for any given result to come back. We haven't talked about that. That has to do with CPU pipelining. And so that's a kind of a thing that we haven't gotten to yet. But anyway, it looks like mul_ps here it's a 5-cycle latency, that looks like, and a 1-cycle throughput. And mul_pd is exactly the same, right? So basically, it's exactly what I said. It's half as fast, right? So I said it was half as fast, and it's half as fast. So I don't know. Whatever the person who wrote in the Twitch chat is, I'm not sure why you were saying that it wasn't massively slower. It's half as fast to do doubles as it is to do singles. So if half as fast doesn't bother you, I don't know what does. That's like the difference between 60 frames a second and 30 frames a second, right? That's massive. But yeah, I don't know. All right. So there we go. Let's see. We're still, you know what? It's kind of a lazy day, and we kind of had an excursion there. I'm going to keep going on the questions. Why not? Let's take a look. What are your thoughts on Swift? I've never seen it. I mean, I know what it is, but I've never seen it. What do I think of Jonathan Blow's programming language? I think it's awesome so far. I really am anxious to see when he actually gets something that he's willing to release. I will be playing around with it. Let's see. What do I think of try dlang.org? I don't know what dlang.org is, but I can certainly look at it. Did you have any discussions with Jonathan Blow and its compiler and what sort of features you'd like to see? Yes, we discuss it all the time. But he and I don't have similar programming styles in some ways, so, you know, I tell him, we talk about sort of things, and I, you know, sort of tell him what the sort of stuff I would like, and we also go over sort of stuff that he would like, and so we definitely talk about it a lot, but he has different goals for the language necessarily in mind than sort of where I would necessarily go if I was doing a language. So I try not to push him. I don't want to make his language into something that is what I would want to see necessarily in a language, because you can't make one language that does everything's thing. And he's going for a very specific thing, and I think he's doing a really good job at that. And so usually when we talk about it, it's less about me saying what I would like to see in his language and more about brainstorming stuff about how to accomplish what he's trying to accomplish in the language, because I would like to see that language be the best at that, because we do definitely need that as well. And so I'm interested in seeing his language go where he wants it to go, not where I want it to go, if that makes sense. Let's see. Do I ever write functions like printf to take variable arguments? Sometimes, but they're usually debugging functions. Would you consider using a templated type-safe version of printf even though you hate templates? No. Templates are never worth the pain, in my opinion. So no matter what they do, I wouldn't probably use them. Let's see. Let's take a look here. If there is one book you would... if it's half as fast only if you do millions of operations. No, it's half as fast as long as you do 5 or more, right? Well, it's half as fast no matter how many you do. because it's exactly the same timing. So if you do any, it's half as fast, right? Whatever the piece of code was, it's half as fast in float, as long as you're doing 4 operations or more. As long as you're doing it on 4 or more floats, it's half as fast. Okay. What low-level language would you suggest to someone new to low-level programming? Well, I think C is usually the one. That's why I'm using it for this stream. Are we using the Win32 API but compiling for 64 bits? Do we need to compile for 32 bits for WinXP support? And it looks like we have Int64 and Real64 in the CPP. So yes, we do need to compile for 32 bits for WinXP support, and we will be doing that. But no, you don't have to worry about Int64s and Real64s because those both work on 32-bit Windows as well. They're just slower. So as long as we don't use hardly any of those, we will be fine. As long as we don't use Int64s and Real64s in super critical code, then we'll be fine. In game development, do you follow enterprise design patterns, or do you have some different design patterns? No, we do not follow enterprise design patterns. Maybe some people, game developers, do. I certainly don't follow any enterprise design patterns. Definitely not. Sorry. What do you use for collections if you do not use templates? I usually use just something hand-coded for whatever the situation is. I didn't get the outcome of the mul ps mul pd compare. The latency packing was the same. How does that end up being double time? Okay, that's a good question. I didn't really go into detail on this because it wasn't really, I didn't really super want to talk about it much because I was just trying to make sure that the person who was writing in the Twitch chat was not correct about it. But basically, because I'd want to correct what I said if it was. But basically what I'm saying here is there's 2 commands that you can issue. Mul ps and mul pd, okay? Both of these commands take 5 cycles to return, right? So 5 cycles to complete, and they have 1 cycle throughput. So you can basically issue them every clock and get them back 5 clocks later, and so you can essentially do 1 per cycle if you get up to speed. But we don't actually care about that at the moment, and we're not going to talk about that much. For purposes of what you're asking, all we need to know is both mul ps and mul pd have exactly the same specified timings in the timing tables. So if you execute a mul ps or you execute a mul pd, it's basically the same, right? The timing. So the reason I said it's half as fast to use doubles, which is this one, this is Real64, and this is Real32. The reason it's half as fast is these instructions are the same width. Both instructions operate on 128 bits worth of data, basically. And 128 bits divided by 32 bits, right, for Real32, means you can pack 4 Real32s into 1 register, right? So basically, mul ps operates on 4 Real32s at the same time. If you call mul ps, you can do 4 floating point multiplies at the same time. Real64s, on the other hand, it's still operating on 128 bits, but now you're dividing by 64 bits, so you only have 2 Real64s that can fit into 1 register. So what I was saying is that if you're doing anything at all, like basically if you're doing any more than 3 operations, then doubles are half as fast. Because basically, as long as you can do 4 of them at once, you will get twice the speed, because this instruction takes the same amount of time as this instruction, but does twice as many multiplies. So hopefully that makes some sense. Let's see. So you say, someone was saying on the stream, if you're writing SIMD code, then you care, otherwise you don't, and what you're writing is not SIMD. So no, that's not true. So yes, this particular very specific example may not be SIMD, but literally the thing we will use it for is totally SIMD. You will have a bunch of cycle counts from all the different places in your program that you sample the performance counter. You will then need to do a bunch of subtracts on them. You will then need to do a bunch of divides on them, or multiplies on them, or reciprocals on them, and you can do all of those completely SIMD because they're exactly the same operations. So no, this will be totally SIMDized, and it will be totally slower if you decide to use doubles. Now, I'm totally fine with someone saying that you won't have enough of these to care about the fact that it's slower, but it is half as fast. That's just the truth. So whenever you write code like this, unless it's literally the only time you think you will ever do it, which for performance profiling we know it won't be. We'll be taking hundreds of samples of RDTSC and not maybe hundreds of the query performance counter, but we'll at least be taking hundreds of RDTSC samples per frame. So if you're going to then do operations on them, if you can move it down to 32-bit, those operations will be twice as fast, period. But if you don't care, if you're like, I don't care how fast that is, I just want to do it in 64-bit, and I know since that we're only doing like 100 operations, maybe that doesn't matter because 100 isn't that many in processor terms, that's fine. But understand the difference between saying you don't care and saying it's not faster, because those are different statements. Let's see. Yes, MSVC will often not pack things without intrinsics for you. Potentially, no, actually, MSVC does have a way of doing that automatically for you if you want to. But yes, we will do all of our own intrinsics for all of our own floating point operations because it's just usually easier to explicitly tell the compiler how you would like to do packed instructions. But no, both LLVM, well, I should say, I have experience with LLVM doing this. I don't know about MSVC, but I believe it also does this. You can auto-vectorize a loop just fine. You don't have to. MSVC will totally output it for you. At least that was my assumption. I know LLVM will. LLVM will trivially output it for you. You can just say that this thing is vectorized, and it has loop vectorization built in. So it just totally does that. So I'm not sure what you're saying that it won't output that. It totally does output that. Maybe MSVC is like behind the times on that, but LLVM is not. And saying that the compiler won't output vectorized code for this is also not true. You just have to do more of them, and it totally could do that. It could totally vectorize this if we had, say, 20 performance counters and we wanted to vectorize them. You could totally have LLVM auto vectorize a loop for you. That's not hard at all. Or IPC if you were using that. I don't know about MSVC because I don't use MSVC a whole lot these days. So whether MSVC will output it, I'm not sure. I thought they had auto vectorization in MSVC, but maybe they don't because MSVC does kind of tend to lag behind. But LLVM will totally auto vectorize that for you. Let's take a look here. And also, Tom Forsyth says he has a rant on double precision. So let's take a look at that since it's right in the stream here. Let's take a look. He says it is at HTTP. Let's see here. I'm going to try to decode this URL 5TBAH. He posted this in the stream. This web page is not available. Tom, what's going on here? Okay, there we go. Okay, so here is the link. You can read it off here. And here is his rant on double precision. So I don't know what it is, basically. I don't know exactly what he's ranting about, but Tom usually has interesting things to say. So if you want to read about his double precision, I will go read it later. Here it is. I'll leave that up on the screen for people who want it. Will we take MSVC all the way to shipping, or will you use LLVM even on Windows? I would already just be using LLVM for everything if you could actually use it on Windows, but right now they haven't gotten to the point where you really can. Basically, if you want to use LLVM on Windows right now, you have to switch to using a GDB-based debugger, like a dwarf-based debugger, and like Qt Creator or something like that, and those are worse than MSVC's debugger and stuff. And basically, like, what I would say is, if LLVM was at the point where I could ship Windows stuff with it, I already would be doing that. There would be no MSVC in the picture, but it's not quite there yet. Believe me, the day that it is there, I am off MSVC so fast because I don't like MSVC at all. I have no interest in using it. But its toolchain is more mature on Windows, and so I have to sort of stay on that on Windows for a number of reasons. But when they get to the point when you can have a totally good experience using LLVM on Windows, I am totally switching. So yeah, if they did that in the middle of Handmade Hero, we'd go ahead and switch for sure. But I don't think they're going to have that ready in the next year or so. Maybe, if we're lucky. I know there's people working on it. So, and you can actually do it. You can compile Windows code with LLVM. There's just a bunch of caveats, basically. What's an intrinsic? So an intrinsic's a thing that we will be looking at later. That basically is, so we kind of, again, this is jumping the gun a bit, but since we're way past time now, we're just kind of having fun on the stream, and I like having fun on the stream. Basically, an intrinsic is just something that tells the compiler, it's something that looks like a function call. And in fact, we've already used one, this one. It's something that looks like you're calling a function. But actually what it is it's a hint to the compiler that what you want it to do is a specific assembly language instruction. And so we can sort of see how that works. Like this looks like a function call, right? It looks like we're calling a function called RDTSC and that function is returning end cycle count. But if you actually step into the call, right here, and take a look at the assembly language that was generated, you will notice that no actual function call has been generated. Instead, what's generated is a straight up RDTC. Pretty awesome, right? So basically, an intrinsic is a thing that allows you to direct the compiler to do a certain thing in assembly language, that it can emit directly in line, that it doesn't have to think about a function call or C programming or any of that stuff. It can just know, oh, he wants me to get the timestamp counter here. I know how to do that directly on the CPU. I'm just going to do it, right? And that's what that is. So the reason we were talking about them for SIMD is because C, unfortunately, was designed a long time before this concept of SIMD. SIMD is, for people who don't know, and we'll talk about this more later, but SIMD is basically an acronym, SIMD. It stands for single instruction, comma, if you will, multiple data. And what it basically means is normally when CPUs were first created, they typically did operations on one thing. So if I say something like this, and I then go z equals x times y, right? This kind of a thing. Makes sense? I expect to see some code outputted that is just going to do a multiply that says multiply x by y, right? So there's one piece of data in x, one piece of data in y. I multiply the two together and I get z. So it's single instruction, single data, essentially. But modern processors have found that it's much more efficient because of the way instructions are encoded, and so that it can know, basically, because you tend to do expensive things, the expensive parts of your code tend to work on big batches of stuff, lots of pixels, lots of vertices, that sort of thing. It tends to be that you want to do the same instruction to a lot of things at once. You want to multiply a lot of values by a lot of other values in a batch. So you don't have to actually issue as many instructions if the processor gives you a way to say, hey, look, I'm going to say one instruction, and I want you to multiply these 16 things by these other 16 things. Just do them all with one multiply. So I can just basically load 16 things into a register, 16 things into another register that's really wide. They're very wide registers. 128 bits, 256 bits, 512 bits, right? Pack a bunch of different values into those registers. 4 floating point values, 8 floating point values, 16 floating point values in one register. So that when I say multiply this register by this other register, it's not just doing one multiply, it's effectively doing 4 multiplies, 8 multiplies, 16 multiplies at a time. So it saves on the instruction encoding, and it saves on the understanding of the logic that the processor has to do, but it could do a lot more multiplies. So that you're basically the arithmetic unit, the thing that's doing the actual multiplies in the processor, can be this huge, wide, giant multiplier that does tons of multiplies in parallel, and the logic that's actually driving it can be very simple. It just goes, okay, we're doing a multiply, 16 multiplies, go. Instead of having to go, okay, grab the two things, do a multiply. Grab the two things, do a multiply 16 times, right? So what SIMD is SIMD is that concept, that there's a single instruction that operates on multiple data multiple things at once and does a symmetric, the same operation to each of those pieces of data. And so typically what it corresponds to is wide registers, registers that you have one name for. So I call this register something, XMM0 or something. I have one name for the register, but actually that register is separated into buckets that contain multiple discrete 32-bit floating point values. Now the reason this impacts our floating point and double situation is because obviously you can fit twice as many floats into the same space as a set of doubles. I'm going to fit 4 doubles in something, I can fit 8 floats in there. So if you're doing SIMD, and the SIMD instructions all took the same amount of time, which as we saw they did in the case of a multiply, then doing it in doubles is half as fast as doing it in singles because you can only do half as many doubles, you can only fit half as many doubles in the register. Hopefully that makes some sense. Yeah, that's a good point. So somebody was reminding us, we stuck O2 in here to ask for optimized build. And what we should probably do is switch back to that because we're not doing optimization yet. So we'd rather have a debug build because debug builds are easier to understand and read. Basically, they're easier to look at because the compiler hasn't rearranged everything and smushed instructions and optimized things out. So when we're trying to learn, it's much better to work in debug mode where the processor doesn't actually do any optimization. Let's have the optimizer off so that we can see everything explicitly. All right, we're running up into the end of the stream here, so last couple questions. Isn't it a pain to work in Windows, especially as a programmer? No more so than anywhere else. I like working in Windows actually the best of any platform because the debugger is the best. It's the best debugger. I like working on Linux because I don't have to fuss a lot with like, I don't have to, every time I install a machine, I don't have to call Microsoft for permission and have it authorize my machine and all this other nonsense. Like I don't have to deal with all of that stuff. I don't have to do all the weird installation process. The package managers and stuff on Linux are really good, that sort of stuff. So there are things I like about Linux better, but the debuggers are awful on Linux. They're just awful. And so I do like programming on Windows probably the best because the debugger is the best. If and when people come out with a really good debugger for Linux, then I think there'd probably be nothing really that I like better on Windows anymore. But it's not really a pain on Windows. No, it's fine. Let's see here. Didn't we want to start adding warnings? Yes, probably Monday. I think we'll turn on a higher warning level, and talk about what that means and why we care. Let's see. I think that's about it for questions on the stream. Yeah, so it looks like that's it for questions on the stream. So thank you so much for joining us for a nice lazy handmade hero, a nice 2-hour handmade hero. Sometimes it's fun to go a little bit long when we have the time for it. Thank you so much, everyone, for joining me. I know that we're not at the normal time, so I feel like probably it's anyone who's on the stream is a rather dedicated handmade heroer, not at our normal 8 p.m. time slot. Hopefully this weekend, again, I keep saying hopefully, but I haven't quite had time to really fully wrestle all the CSS. Web programming is so slow, in my opinion, because of all the wrangling to try and get things to look okay when you're using other people's code and stuff. So we're still on the email, so if you want to email a question, you got to email in here. That'll be changing to forums just as soon as I can finish up the CSS nonsense. Again, if you would like to follow at home with the source code and the art assets as we start to have them, if you'd like to pre-order the game, you can pre-order it here, and that gives you a link where you can always download the latest source code and latest art assets as we start to work with art assets coming next week and so on. So handmadehero.org is your source for anything that you actually need. You can also get to the video archive and the Twitter where we post times and stuff like that. So check that out. And otherwise, thank you very much for joining us. I hope to see you here for the next stream, which will be Monday at 8 p.m. Pacific Standard Time. Hope that you have enjoyed this stream, and we will see you then. Thanks, everyone, for joining us.